Welcome to this explainer. If you're looking to totally demystify one of the most notorious, FANG-level technical coding problems out there, well, you're in exactly the right place. Today, we're tackling the next permutation algorithm. I absolutely love this problem, honestly, because it's the perfect example of how a terrifying, mathematically massive challenge can be completely tamed by just a few brilliant, simple observations. We're going to break this down from first principles and build an intuition so strong you'll literally be able to code it in your sleep. Let's get into it. Okay, let's map out our progression for today. We're going to start by defining the next permutation problem, then we'll look at the brute force trap, build up our dictionary order intuition, step through the optimal algorithm, and finally, lock in our time and space complexity. Section 1, the next permutation problem. Let's define the challenge. So, to make sure we're building our understanding from absolute first principles, we have to ask a very basic question. What exactly is a permutation? You know, it's a word that gets thrown around a ton in computer science, but let's just strip away all that academic jargon. At its core, a permutation is just a rearrangement. Imagine you're handed an array of three simple integers, 3, 1, and 2. How many different ways can we arrange those exact three numbers? Well, basic math tells us it's 3 factorial, 3 times 2 times 1, which equals 6. So there are exactly 6 possible unique variations or rearrangements for this specific array. Now, to find the next permutation, we have to look at these arrangements in what we call dictionary order. Think of it like treating these number sequences exactly like words in a dictionary, sorted sequentially from the absolute smallest to the largest. Like 1, 2, 3 naturally comes before 1, 3, 2, right? Just like the word apple comes before axe. So finding the next permutation simply means finding the exact sequence that immediately follows your current array in this sorted ascending dictionary order. Section 2, the brute force trap. This is why the obvious answer completely fails.
If you're just following the direct brute force logic of the problem, you might naturally suggest a 3-step process. First, use recursion to generate all possible permutations in sorted order. Second, do a linear search to find exactly where your current array sits in that massive list. And third, just return the array sitting at the very next index. Now, stating this conceptually, that shows competence. It proves you understand the end goal. But if you actually try to write the code for this in an interview, it will absolutely destroy your chances.
And why is that? Because of this massive number. Think about it. If you're given an array of just 15 elements, generating all permutations takes an n factorial time complexity. 15 factorial is roughly 10 to the power of 12 iterations. That is a terrifying amount of computational time. We're talking about an algorithm that would take hours, maybe even days to run. It completely proves why an O of n factorial time complexity is totally unacceptable in the real world. Moving on to section 3, dictionary order intuition. Let's start building the linear logic. And this brilliantly illustrates our core intuition. Let's look back at the English dictionary. Why does the word Raj appear before Rex? And for that matter, why does Rex appear before Arbex? Well, it's all about prefix matching. Raj and Rex share a long prefix. The letters R and A. The sequence only changes at the very last letter. You see, the English dictionary proves that next elements tend to share the longest possible prefix before changing a single solitary character. We can actually apply this exact same English word logic to our numbers. We want to keep the longest prefix possible, which means we want to modify the numbers at the very end of our array first. That is exactly why we must search the array from the back, scanning from right to left. We are looking for the precise spot where the sequence breaks its increasing pattern. Basically, we're looking for a dip. So the absolutely crucial point here is defining this dip, which we're going to call the breakpoint. The breakpoint is the first index, let's call it I, when scanning from the right, where the element is strictly smaller than the element immediately following it. This single mathematical observation is the turning point of the entire algorithm. It tells us exactly where our long prefix ends and exactly where we need to make our change. Section 4, the optimal algorithm. These are the 3 steps to an O of n solution. I am so incredibly excited to share this because it's just pure elegance. We can completely circumvent the need to generate those massive full permutations by following 3 magical steps. Step 1, find the breakpoint index, our dip. Step 2, swap that breakpoint with the smallest greater element to its right. And step 3, reverse the remaining right side elements. Let's walk through exactly how this works. Let's watch this scan in action. Take the array 2, 1, 5, 4, 3, 0, 0. If we start scanning from the right, we see 0, then the other 0, then 3, 4, 5. The numbers are steadily increasing, but then, boom, we hit the number 1. Suddenly there's a dip. 1 is strictly smaller than 5, so 1 is our breakpoint. Now what's really interesting here is that everything to the right of the number 1 is in strictly decreasing order, meaning absolutely no larger prefix can be formed over there. But wait, we do have to address a major edge case here. What if we scan from right to left and there's no dip at all? What if the array is just 3, 2, 1? Well, that means the entire array is already in descending order. It's the absolute highest, very last permutation possible. In this case, as the rule states, you simply fall back to the first possible rearrangement. You literally just reverse the entire array to get 1, 2, 3, and you're completely done. But assuming we did find our breakpoint, the number 1 from our earlier example, we move right into step 2. We need to swap that 1 to make the prefix slightly larger. But look at the right side, 54300. Which number do we actually swap with a 1? Well, we need the number that is greater than 1, but is the smallest possible number that fits that description. In this specific case, it's the 3. Swapping the breakpoint 1 with the slightly larger 3 minimizes the increase. This ensures we land on the immediate next permutation rather than jumping way too far ahead to a completely wrong answer. And now for the final stroke of genius. After our swap, our prefix is slightly larger, but the right side of the array is still in descending order, 54100. To make this the immediate actual next dictionary permutation, we need those right side elements to be as small as possible. And because they're inherently decreasing already, a simple reverse operation sorts them entirely in place to ascending order, 00145. That right there perfectly completes our optimal algorithm. Section 5, time and space complexity. Let's tie a bow on this interview. Let's see how all this builds our final complexity analysis. We have successfully transitioned from a disastrous O of n factorial nightmare down to a beautiful flat O of n linear time complexity. And why? Because we only did 3 simple linear passes. 1 to find the dip, 1 to find the swap, and 1 to reverse the rest. That's roughly O of 3n, which just simplifies right down to O of n. And as for space complexity, well, we did every single modification entirely in place. We didn't create a massive array of arrays. We just swapped and reversed, giving us a perfectly clean O of 1 constant space complexity. Think about what we just did. You took a problem that looked mathematically impossible to optimize, and you solved it with a dictionary, a dip, a swap, and a reverse. By truly understanding the why behind the logic, you've memorized the solution without having to memorize a single tedious line of code. Keep practicing these deep intuitions. So, are you ready to absolutely ace your next data structures and algorithms interview? Because with insights like this, you for sure are. Thanks for joining me for this explainer, and keep on learning.